Welcome back, and in the last video we were talking about coyotes and roadrunners and how that population changed over time, and we defined that system as a dynamical system because, again, the populations were kind of codependent. So the population for the next year relied on both the current population of each of the subpopulations. So now we're just going to kind of investigate the mathematics behind this. Okay, so again, the matrix that we were looking at before, I'm just going to give it a name of A, and here you go, it's written there, and now we're given initial vectors, and just for notation purposes, sometimes when we're dealing with dynamical systems, we get a little bit lazy. Instead of writing x of 0 like that, we just do a subscript. Okay, just be aware of the two notations. Okay, so again, we want to find x1, x2, x3 with this initial state vector. So we can look at x of 1 and x of 2 and then x of 3. Okay, x of 1, again, you can do the calculation here. You end up getting 11, 10, and 330, which, if I think about it in terms of the initial state vector, right, 100 and then 300, I'd have to multiply that vector by 1.1. Okay, and then x of 2, okay, this, if I do the calculation, ends up being 121 and then 363, which, again, in terms of the initial state vector, is 1.1 squared. And now, with that, I think you can start to see where I'm going. You could do the calculation here for x3, but what it would end up giving you is 1.1 to the third times 100, 300. Okay? And then so we might conjecture that x of n is just going to be this 1.1 to the n times 100, 300. Now, it isn't completely clear why 1.1. You're going to have to take on a faith for right now. Okay, that's just something I'm going to need you to do for right now. Okay, we'll see it pop out later. Similarly, if you do this exercise number 2 with a different state vector, x1 ends up being 180 and then 90, which, again, in terms of the initial state vector, we can say, okay, well, that's going to be 0.9. Okay, and then sure enough, if you do x2, x3 up to xn, it is just going to be 0.9 to the n, and then 200, 100. Now, again, why 0.9? We'll see it in a moment. Okay, i.e. in the next few videos. Actually, the next video. Okay, but now, from all this, this is fine, but we kind of want to know, okay, well, xn, right, that's an arbitrary stopping place. Like in calculus, we can do limits and all that stuff. Why not do the limit of this? And, well, that's the idea here. What happens if we allow t to extend forever, both forward to time infinity and then backwards? So if we were to look back in time too, what would happen? And what do we see in our plot? Okay, so now I'm going to show you another set of images. So here you might recognize the blue dots and the orange dots from our first video where we were looking at, this was like the initial 1,000 for each, 1,000, 1,000, and then this one was like 1,400 and 750 or something like that. And so we were looking at these trajectories over time and what was happening with those. So now, and then this pink one, we didn't show you that, but that would just be an intermediate spot, maybe like 900, 900. Okay, but anyway, progressing. So we see the two curves. If we were to have a continuous system, right? We don't have a continuous, we have discrete sets. Because we're stepping by whole years, not partial years. So anyway, if we allowed it to be very continuously, this is what it would look like. And it would kind of approach these two lines in green and red. Not clear what they are or why they are appearing right now, but that's what we would see. And sure enough, if we had other starting positions, so again, this is still coyotes and this is still roadrunners, this is what we would see over time if we picked different starting positions. So watch those over time. Here's after one step, 2 steps, 3, and more, and even more, and more. Okay, And again, now this is stepping incrementally by whole years. If we allowed ourselves to step continuously, here's what we would see. This is called a phase portrait. So we will be constructing these. We'll do this formally in the end of the section just so we have all the different pieces of terminology down. But this is what we would see over time. Again, and we would likely have only one of these depending on our initial populations. So we just need to watch that and be mindful of where we start, because that's going to vary. Our end results is going to vary based on where we start.